model and solve problems. So we're going to look at applications of set theory. Now, we've got to extend the principle of inclusion and exclusion to 3 sets. Because now we're going to look at 3 different sets and all of their overlap. So it looks like this big, long process, but let's just break it down here. We're going to look at the union of sets S, T, and C. We're going to add the number of elements from each of their sets. That's the same thing that we were doing before when there was just 2. Then we're going to subtract the intersection of each of the sets. So this time though, we've got S will intersect with T, S will also intersect with U, and then T will intersect with U. So you have to subtract all of those intersections. But notice, this intersection point right here, of all 3 of them, gets subtracted out 3 times. So we actually have to add that little part back in. We'll show you how this will work. So here, we've got some clues. We've got a problem to solve. We've got 28 children have a dog, a cat, or a bird. 13 of these children have a dog, 13 have a cat, and 13 have a bird. So obviously, we have 13, 13, and 13, that's 39. That's more than the 28 children. So some have more than one of these. There is some intersection. 4 children have a dog and a cat, 3 have a dog and a bird, 2 have a cat and a bird. No child with 2 of each has a pet. That's important. So, some of them, though, could have all 3. And that's what question A asks. How many have a cat, a dog, and a bird? And then how many have only one pet? So we're going to need to draw a Venn diagram for this to sort it all out. And again, if you can do it without a Venn diagram, and it doesn't ask you specifically to draw one, go ahead. So we're going to let P represent the set of children with pets. Right? So that is our universal set. So these are children with pets. Then we're going to have those that have birds, those that have a cat. And we've got to make sure that they all intersect here. Those that have a dog. So there are our sets. Now, 13 children have a dog. We can't start there because some of those numbers are going to fit into overlap. We need to start with the most overlap and work our way out. We don't know how many children have all 3, so we're going to let that be X for now. That's what we're actually have to find in part A. What we do know is that 4 children have a dog and a cat. Specifically a dog and a cat. So there's our overlap for dogs and cats. 3 children have a dog and a bird. 2 children have a cat and a bird. So we do have some overlap there to work with. Now what we're going to have to do is we're going to have to use that principle of inclusion and exclusion to figure this out. So what we do know is the number of children that have dogs is 13. The number of children that have birds is 13. The number of children that have cats is 13. Now we need to start subtracting their overlap. Now the intersection of a bird and a cat is not just 2, it's X plus 2. Alright, this is all part of the intersection of birds and cats. It's the sum of it also happens to be the intersection of all 3. Then if we look at birds and dogs, birds and dogs would be X plus 3. Then the intersection of cats and dogs would be X plus 4. So we have to subtract all of those intersections. Then we have to add back the intersection of all 3. Because remember, it got subtracted out 3 times, which is too many. And so we have to put that back in. So it's plus X. And we know, after all of this, that there are 28 children in total that we have surveyed. So now we have an equation that we can solve. This takes you back to grade 9. So let's go through and solve this equation. We have 39 minus x minus 2 minus x minus 3. Remember the negative distribution to the bracket, that's what we're doing. Minus x minus 4 plus x equals 28. If we were to go through and collect up all of our like terms, we will end up with 30 minus 2x equals 28. 39 subtract 2 is 37. Subtract 3 is 34. Subtract 4 is 30. That's where the 30 comes from. Negative x subtract x is negative 2x. Minus another x is negative 3x. Plus an x is negative 2x. So now we are going to subtract 30 from both sides. Negative 2x equals negative 2. Divide by negative 2. X equals 1. So there was one child that had a cat, a dog, and a bird. So we can now go back and we can complete our Venn diagram. And then we can ask questions about any of these. So 13 children have a dog. Right now, in that circle, there are 8 kids that are already accounted for. So therefore, 8 plus 5 is 13. There are 5 kids with $50. There were 13 kids with cats. If you look already, we have 2 plus 1 plus 4 is 7. So 7 plus 6 is 13. There are 6 that only have cats. And then if you look at the bird, there were 13 children that had a bird. In the bird circle, there are already 6 children accounted for, so that leaves 7 more. So now, how many children have only one pet? 7, 5, and 6. If you add those up, then you have 18. So 18 children have only one pet. You can extend your knowledge of Venn diagrams and threefold inclusion and exclusion to more than just two sets. And just work your way from the innermost overlap out. Set theory is also useful for solving many types of problems, including internet searches, database queries, data analysis, games, and puzzles. You can use concepts related to sets to search for websites on the internet. We can put an exact phrase in quotation marks. So if you want to search and you want that exact phrase to appear in your result, put it in quotation marks. We can connect words or phrases with and to search for sites that contain both. So if you want sunshine and boating, you want to find places with both of those. You're going to use the word and you'll get results that will have both of those in it. The word and represents the intersection. If you connect the words or phrases with or, then you're going to get sites that contain either one or the other or both. Alright, the word or represents the union of 2 or more sets. So that's going to give you a much broader search than putting the word and. To further reduce your hits, you can enter a minus sign immediately before any words or phrases you want to avoid. So if you don't want a particular word or phrase to show up, you would put a minus sign in front of it. So let's have a look here, and let's try one. We want to find a recipe for chocolate chip cookies, but I want it like your grandmother used to make. So we're going to go through, we're going to do some searches, and we're going to see how using set theory will narrow down your results. So we're going to go to the internet and we're going to search chocolate chip cookie recipe. And we're going to see how many results come up when we search this. About almost 12 million, 11,900,000 results came up. Do we really want to look at all of these recipes? That's a huge amount of results. So what we're going to do is we're going to see if we can shorten it. Because notice what happens here. This second one right here, it's just a cookie recipe. All right, so we're going to have different results. Let's just have a look at what else we have here. Chocolate chip cookies. It doesn't even have the word recipe in it. If you were to continue going down, you're going to get some different results. It was pretty broad. What we're going to do is we're going to put this in quotation marks. So now I want exactly those words. And I'm going to search it. We're going to see if we have less than 12 million. That pop up this time. Look at that. We went from 12 million down to about 536,000. Huge reduction by putting things in quotation marks. All right, because now we only got results that have that phrase in it. Now, if we go back and look at what we're doing here, we're on C. Remember that you just suddenly remember that your grandmother's recipe contained oatmeal and pecans. So we want to search chocolate chip cookie recipe and oatmeal and pecans. So we want it to have that exact phrase, so we leave it in quotation marks, but now we want to find the intersection of those that also have oatmeal and pecans in them. So I'm going to go back here, and then we're going to add and oatmeal and pecans. And we're going to search. So remember we were at 536,000, and look, now we're down to 61,000. So we're really starting to limit our results by looking for intersections, by narrowing things down. So now we're down to 61,000. Now what we remember is we dislike walnuts. So now we want to search for the chocolate chip cookie recipe that has oatmeal and pecan, but we want to take the walnuts out. So remember, we can subtract walnuts. So I'm going to go subtract walnuts. So we're at 61,500. Let's see what happens when we look for recipes that do not have walnuts in them. See if it will search. About 44,000. So we went from 61 down to 44. So we eliminated all of the ones that had walnuts in it. So as you can see, the more specific you get, the smaller your results are going to be. So step theory works in something that you guys probably use on a regular basis in doing internet searches. So this may assist you with narrowing things down. What we ended up searching for, if we look at this in a Venn diagram, notice how we started really broad, all search results. But then we went down to C, which is chocolate chip cookies. So our black oval there. And then we started refining the searches and looking for overlap. We didn't want anything with walnuts. We wanted pecan and oatmeal. So our final result is just this little area that's highlighted in yellow. The internet has an application where you can use set theory to help you search for things.